So this video is about replication lag that can happen between a leader and the followers in a distributed system. Now let's understand in detail what this term replication lag means and what problem can we have because of this lag. So in a read scaling architecture, you can just increase the capacity for serving the read-only request by simply adding more followers or more follower nodes. However, this approach only realistically works with asynchronous replication. This is because if you try to synchronously replicate to all followers, then a single node failure or a network outage would make the entire system unavailable for writing. And the more nodes you have, it's likely that one node will be down. So a fully synchronous configuration would be very unreliable. Now, if an application reads from an async follower, it may see outdated information if the follower has fallen behind, and this leads to inconsistencies in the DB. For example, if you run the same query on the leader and a follower at the same time, you might see different results because not all the writes have been reflected in the follower. So this inconsistency is just a temporary state. So if you, let's say, stop writing to the database and wait for a while, all the followers will eventually catch up and become consistent with the leader. So for this reason, this effect, it's also known as eventual consistency, because it means that the follower will eventually catch up with all the they will catch up with the leader node. So in general, there's no limit to how far a replica can fall behind. So this delay between the write happening on the leader and being reflected on the follower, it's called the replication lag. So this replication lag, it may only be a fraction of a second and might not be noticeable in practice. However, if the system is operating near capacity, or if, let's say, there's a problem in the network, this lag can increase to several seconds or minutes. So next we'll see three examples of problems that can occur when there's a replication lag, and also we'll see some approaches to solving them. So this is the first issue that we can see because of the replication lag between the leader and the followers. So this is called reading your own write. So to illustrate this with an example, there are many applications that let the user submit some data and then view the data that they just submitted. So this can be a comment on a discussion thread on a social networking site, or let's say if you change your profile picture on Facebook or LinkedIn. So when this new data like the comment or the picture is submitted, it must be sent to the leader node. Now, when the same user, it views the data, it can be read from a follower node also. So with async replication, there's a problem here, because if the user views the data shortly after making that write, the new data might not have reached the read replicas. So to the user, it looks like as though the data that they just submitted, it was just lost. So they will be very unhappy in this case. So in this diagram, let me get the pointer. So in this diagram, there's a user who is trying to submit a comment on a post. So this is the query, insert into comments. So it goes first to the leader node here. L is the leader node, and F1 and F2 are the follower nodes here. So the leader node, after some time, it will also replicate the data to the two follower nodes. So this is the path where it goes to follower 1, and this is the path where it goes to the follower 2. Now, since this is a sync replication, so in this case, as you can see, the leader, it does not wait for a success message from the followers. So in this case, the leader will just send it will send an OK message to the user that your comment has been posted. So now let's say before the comment is actually reflected in the followers database, let's say a user is trying to read the comment. So in this case, it will send this read request to this follower F2. Now, since this follower DB, it's not updated because of the replication lag, because of this replication lag, it's going to be updated at this point of time, and the query is made before that. So because of this replication lag, user won't even see any results. So to the user, it will look like that the comments, they have just disappeared. So that's why it's called read your own writes, because user has to read what they just wrote or submitted. So to handle this situation, we need read after write consistency, also known as read your writes consistency. This is a guarantee that if the user reloads the page, they will always see any updates they submitted themselves. Also, it makes no promises about other users. For example, other users' updates may not be visible until some time. However, it assures that the user that their input has been saved correctly. So let's see how we can implement read your write consistency in a system with a leader based replication. One approach is that when reading something that the user has modified, it's read from the leader. Otherwise, it goes through the follower node. For example, a user profile information on a social networking site like LinkedIn or Facebook, it's only editable by the owner of that profile and not by anyone else. So the simple rule is that the system always read the user's own profile from the leader node. And when we want to read any other's user profile rather than my own, it can be read from a follower. Because in this case, if I edited my own profile picture and I try to read it from a follower, the follower might not have data because of the replication lag. Now let's say if most of the things in that application are editable by the user, then our first approach won't be effective at all. This is because most things would have to be read from the leader node, and this will totally negate the benefit of read scaling. So in that case, we have this another way to track the time of last update. So for example, let's say the system knows that it takes about 1 minute for all the writes to be replicated on the followers. So now we can track the time of the last update that happened. And for that 1 minute after the last update, we can make all the reads go through the leader itself. So after 1 minute, now we are sure that all the followers will have the updated data. So the reads can now go through the followers. Now a third way is that the client can remember the timestamp of the most recent write that it has sent to the leader node. So in that case, the system can ensure that the replica that is serving any reads for the client, it has all the updates at least until that timestamp. So let's say if a replica is not sufficiently up to date, now either that read can be handled by another replica or the query can wait until the replica is totally updated. So there can be some issues while implementing read your writes consistency. For example, complication will arise if the same user is accessing a service from multiple devices, for example, a desktop web browser and a mobile app. So in this case, we'll have to implement and provide cross-device read after write consistency. So what it means that if the user enters some information on one device and then they view it on another device, they should see the information that they just entered. So in the approach where we remember the timestamp of the user's last update, this will be difficult. This is because the code running on one device, it doesn't know what updates has happened on the other device. So this metadata about the timestamp, it will have to be centralized. Also, if your read replicas are distributed across different data centers, there is no guarantee that the connections from all the different devices will be routed to the same data center. For example, the user's desktop computer, it uses the home broadband connection, and the mobile device, it uses the cellular network. So it might be completely running on different network routes. So if your approach requires always reading from the leader, then you first have to route the request from all of the user's device to the same data center. So one second example of an anomaly that can occur when reading from async followers is that it's possible for a user to see things moving backward in time. Now let's see how this strange thing can happen. For example, in this image, user 2345 here, it's trying to make the same query twice. So first it tries to make the query to this follower F1 and then also to the follower F2. Now the follower F1, it has a little replication lag, as we can see from here, because this leader, it transfers this message here to this follower F1, and to reach the follower F2, it takes a much longer time. So this first query, it returns a comment that was recently added by the user 1234 here. So but this second query here, it won't return anything because this lagging follower, it has not picked up the write by this leader yet, because after this follower 1 is synced, this first query is made, and this second query is made even before this F2 has synced. So in effect, this second query is observing the system at an earlier point in time than the first query. So it's very confusing for this user 2345 if they first see user 1234's comment appear and then they see it disappear again. So this feels like going backward in time when the comment didn't even exist. So monotonic reads is a guarantee that this kind of anomaly doesn't happen. So when you read data, you may see an old value. Monotonic reads, it only means that if a user it's making several reads in sequence, they won't see the time go backward. So they will not read older data after having previously read the newer data. So one way to achieve this, achieve monotonic reads, is to make sure that each user always makes their read from the same replica. So different users can read from different replicas. So for example, the replica can be chosen based on the hash of a user ID rather than randomly. So for each request, hash ID for a particular user ID, it will always be the same. So yeah, but however, if that replica fails, then we'll have to reroute the user's queries to another replica. So this is how we can implement monotonic reads. Now one third example of replication lag anomaly, it concerns with violation of causality. So imagine this conversation happening between two people. So the first, this conversation here. So the first question that Mr. A asks is how far into the future can you see? And he poses this question to Mr. B. Then Mr. B replies at about 10 seconds usually. So now there's a causal dependency between these two sentences. And by causal dependency, it means that the second statement it's dependent on the first statement. So the second statement, it won't mean anything until this first question is asked. So now imagine there's a third person who is listening to this conversation through one of the follower nodes. Now if things said by Mr. B, it goes through a follower which has a little replication lag. But let's say the question which Mr. A asked, it goes through a node which has a longer replication lag. So now the observer would hear this conversation in this way. The image on the second image here. So they would hear the answer before even listening to the question. So to the observer, it looks like that Mr. B is answering the question before Mr. A has even asked it. So this is what violation of causality means. So preventing this kind of anomaly, it requires another type of guarantee which is known as consistent prefix reads. So this guarantee says that if a sequence of writes happen in a certain order, then anyone reading those writes will see them appear in the same order. Now this can work, but this is a particular problem in sharded databases, because so if the database always applies the writes in the same order, then reads always see a consistent prefix. So this anomaly won't happen. However, in many distributed databases, different partitions they operate independently. So there is no global ordering of writes. So when a user reads from the database, they may see some parts of the database in an older state and some in a newer state. So one solution again to fix this is to make sure that any writes that are causally related to each other, they're always written to the same partition. So there are also algorithms that explicitly keep track of such causal dependencies. So we'll see these algorithms in the later videos in this chapter. Now when working with an eventually consistent system, it is worth thinking about how the application behaves if the replication lag increases to several minutes or even hours. If the answer is no problem and we can work with replication lag, then that's great. However, if the result is a bad experience for users, it's important to design the system to provide a stronger guarantee. So single node transaction, they refer to the traditional approach where a transaction, like a sequence of operations, it's executed on a single node itself, like a single machine or server within a database system. Now this will of course allow for strong consistency, meaning that the database guarantees that each transaction is isolated and appears to be executing sequentially. But many systems, they have like completely let go of single node transactions because they believe that the performance and availability costs that are associated with maintaining strong consistency, they're too high. So most big systems, they argue that achieving strong consistency in a distributed system, it can lead to a decrease of performance and also availability. This is because there's too much cost involved in the coordination and also synchronization between these nodes. So therefore they advocate for eventual consistency always as an acceptable compromise in terms of scalability and performance in distributed systems.